Alright guys, welcome back. Looking at an example here of a voltage controlled voltage source. So this is a dependent power source like the last couple of examples, and basically what we want to do is we just want to figure out what the voltage drops across each element are, and the power dissipation in the resistors, and the power delivery into the circuit through the power sources. So we have one dependent power source, which is here. This is the voltage controlled voltage source. It puts out a voltage that is 1/4 of the voltage of the controlling voltage, which is the voltage across this element. So we have to find that first before we can proceed. And then there's also two other power sources. There is an independent current source here and an independent current source here. So we're going to be applying Kirchhoffs current law, Kirchhoffs voltage law, and Ohm's law throughout the problem. And basically at this point you just want to eventually try to figure out what's going in here with the controlling voltage. So we can investigate this junction first. Because we know there's 1 amp of current flowing out, this independent current source just basically forces 1 amp no matter what to be going through this branch. And same with this one up here, it's forcing 2 amps. So we know that 2 amps are going out this way. And then according to Kirchhoffs current law, what comes in must go out basically. So we have a total of 3 amps going out, so we have to have a total of 3 amps coming in. Okay, so now we know that there is 3 amps of current in this branch here. So we can apply Ohm's law actually to this resistor now, which is V equals IR. So we have the current, which is 3 amps, times the resistance, which is 4 ohms. And that gives us a voltage drop of 12 volts across that resistor, which means that Vx is 12 volts. And we can also determine what the positive and negative side is because the current is flowing into the positive side of all resistors, so we're going to have positive here and negative here. And then we just multiply 1/4 times 12 volts, and that gives us a total of 3 volts for our dependent voltage. So we can also indicate at the other junctions what some of the currents are. We can see here that the current is still going to be 1 amp, because there's just 1 amp of current flowing through here. And same with here, the end of this branch is going to have 2 amps. And we also have 3 amps coming out here, as we said before, going through this resistor. Now in this particular problem, the next step is to find out, again, the voltage drop across something else, and it's going to be this resistor here. We can determine what this is because we actually know the voltage drop across the dependent power source. It's 3 volts. So because the top is the plus side, that means that everything connected to here is 3 volts higher than whatever's connected to the bottom side. Okay, maybe let's color these on just to make it super clear. So this is all going to be one node, like this. And then on the other side we have one single node here that's all shaded in blue. I guess we can shade on the other node that's up here as well, but this isn't really important to what we're talking about at the moment. So the red node, like I said, is 3 volts higher than the blue node. So that means that this is the plus and this is the negative side. And that the voltage, again, as you go from here to here, the difference is 3 volts. So we can apply Ohm's law at this point. So we just have V equals IR. Well, the voltage drop is 3 volts, and we can just divide that by the resistance, which is 1 ohm, to give us what the current is. And 3 divided by 1 is just going to be equal to 3 amps. And again, this is a resistor. We know the plus side is over here, and the current is going to enter the positive side and out the negative side. So we can label on that our current here is 3 amps going down. That means that there's 3 amps here, and then 3 amps coming into this junction as well. Okay, so now at this junction we have 3 amps coming in plus 1 amp coming in, so we have to have 4 amps coming out. So it's going to be going up like this, and that means that there's 4 amps going in here as well. And then at this junction, if we have 4 coming in and 3 going out, then there has to be 1 going this way for Kirchhoffs current law to add up, and then that's also going to be coming in here. So at 1 amp, and then that confirms that we've done it right because we have a total of 3 amps coming in and 3 amps going out. Okay, if you want, it helps to draw a ground sometimes. You don't have to, but we can ground one of the nodes. There's only 3 options here, and you can do a little bit of trial and error, but it doesn't really matter which one you pick. I already know that this is going to be the best one, but basically if you pick another one, you're just going to get negative voltages. And you can just try by trial and error until you get, like, you set your ground to be 0 and everything else will have a positive voltage. So if we set this node, the yellow node, to 0 volts because it's grounded, then when we go across this resistor, we know that we're jumping up by 12 volts because that's what we have already calculated. So that makes the red node 12 volts higher than the yellow node. So I'll just put a 12 over here. And then we can look at either the resistor here or the dependent power source and see that the voltage drop across them is 3 volts. So when we go from the positive side to the negative side, we drop down, which makes the blue node 9 volts higher than ground, or 3 volts less than the red node. So we can just label on somewhere down here that this whole thing is 9 volts above ground. Okay, so that does mean that the voltage drop across this top power source is going to be 12 volts. The voltage drop across the other independent power source is going to be 9 volts as we go basically from 9 to 0. The voltage drop across here we already have is 12 volts, so let's just kind of indicate that here. The voltage drop across the dependent power source is 3 volts, and then also the voltage drop across this resistor is 3 volts. So now let's just calculate the power dissipation of the resistors, and the easiest formula for us to use is just going to be P is equal to VI. So for the 1 ohm resistor over here, we can set up our expression. We have P is equal to VI, so the voltage is 3 volts and the current is 3 amps. So we're going to get a power of 9 watts. And then for the other resistor, which is the 4 ohm resistor, we just have 12 volts times the current, which is 3 amps, and that gives us a total power dissipation there of 36 watts. We can sum those together, and then we'll just get the total is positive 45 watts of power dissipation from the resistors. Now we can do the same thing. We want to calculate the power delivery basically being put into the circuit from the power sources. So let's start with the power source up here, which is the independent current source. And the power is going to be equal to the voltage, which is 12 volts, times the current. And in this case, we're going to put this in as a negative 2 amps. And we do this because of the passive sign convention. Basically, when current enters into the negative terminal of an element, we treat that as negative in this expression. So this gives us negative 24 watts of power being delivered by that power source. Let's do this one next. So we have power is equal to 9 volts times negative 1 amp. So that's a total of negative 9 watts. And then for the dependent power source, power is equal to 3 volts times negative 4 amps. And that is just negative 12 watts. And when we sum those up together, we find that the total power delivered to the circuit is negative 45 watts. And this is what we're expecting because the total power delivery and dissipation should net out to 0 in a circuit. So this is a really strong indication to us that we've actually done everything correctly, and we can be pretty confident with our answer. So yeah, that was just one other example on dependent power sources. In this case, it was a voltage-controlled voltage source. Once you basically figure out what the dependent voltage is based on the controlling voltage, then you can solve it just like any other problem. So yeah, thanks for watching, and I will see you in the next one.